Good morning. There are some more examples on Taylor series for you. Expand fz equal to z minus 1 over z plus 1 in Taylor series about z equal to 0. Of course, we don't have to add and subtract 0. That looks so absurd. So we are having a function fz as z minus 1 over z plus 1. We just take the denominator in the inverse form, that is 1 plus z inverse, and just now expand the series z minus 1 into expand the series 1 plus z inverse. We'll be getting this 1 minus z plus z square minus z cube up to infinity. Remember, this series can be expanded for this mod z less than 1. So we should write for mod z less than 1. Next, which is equal to, if you multiply the terms within, and we'll be getting this series z minus z square plus z cube plus minus 1 plus z minus z square up to so on for mod z less than 1. Collecting the terms with the same powers, we'll be getting the result. Next example, expand fz equal to z minus 1 over z plus 1 in Taylor series about z equal to 1. So now we need the expansion in z minus 1, because about z equal to 1 we have to find, so expansion will be in z minus 1. But we are having the denominator as z plus 1. So can I write z plus 1 as z minus 1 plus 2? Right. So I will be getting now expansion in z minus 1. Taking 2 outside, I will be getting z minus 1 by 2 into 1 over 1 plus z minus 1 by 2. Yes, z minus 1 comes. Now I take this denominator in inverse form and then expand. So this is equal to z minus 1 by 2 and 1 plus z minus 1 by 2 in inverse form denominator. So this is z minus 1 by 2 expanding 1 minus z minus 1 by 2 plus z minus 1 by 2 whole square minus z minus 1 by 2 whole cube up to so on. For, of course, I have to write this whole mod z minus 1 by 2 should be less than 1. So series is expanded for this mod less than 1. Now multiplying this z minus 1 by 2 wholly inside. So this is z minus 1 by 2 minus z minus 1 by 2 whole square plus z minus 1 by 2 whole cube, so on. For taking 2 on the other side, mod of z minus 1 less than 2. This is also taken to be as a region for validity. Next is expand 1 over z plus 1 into z plus 3 in a series valid for mod z less than 1. Now it is given that your mod z is less than 1. Separating the denominators into two parts and multiplying 1 by 2 with the first term, multiplying 1 by 2 with the second term, but you have to take 3 outside before that. Taking 3 outside will be getting 1 over 1 plus z by 3, and 3 multiplied with 2 will be getting 1 by 6. So this is equal to taking the denominators in your inverse form, and before the expansion, let's check. Now for this z plus 1 inverse, it is given mod z is less than 1, so I can expand this first. This is 1 minus z plus z square minus z cube, so on. Now what about mod of z by 3? Let's check mod of z by 3. Mod of z less than 1, it is given, so this is less than 1 by 3, and 1 by 3 itself is less than 1. So now I can expand the other series, because mod of z by 3 comes out to be less than 1. So this is 1 minus z by 3 plus z by 3 whole square, so on. multiplying 1 by 2 with the first series and 1 by 6 with the other series, and taking the terms common, having the same powers, collecting all those terms. So you will get this equal to 1 by 2 minus 1 by 6 plus minus 1 by 2 plus 1 by 18 z plus 1 by 2 minus 1 by 54 z square, so on. This is equal to final 1 by 3 minus 4 by 9 z plus 13 over 27 z square. You don't need to solve all the terms, just few terms, plus so on. Right? Finish. Next. Expand z plus 1 over z plus 2 into z plus 3 in non-negative powers of z and discuss its validity for mod z less than 2. Now it is given mod z less than 2. First separate this denominator and then taking this 2 common, and from here 3 common. So if I take 3 common, I will get 2 by 3 outside and 1 plus z by 3 inverse. Then for the first term, taking 2 outside, will be getting minus 1 by 2 into 1 plus z by 2 inverse. Now first check whether mod of z by 3 is less than 1 or not, and mod of z by 2. Let's check. As mod of z by 2, this is, it is given mod z less than 2. Can I write this upper part, mod z, this is less than 2, and then 2, this is equal to 1. Yes, mod of z by 2 comes to be less than 1. For the second part, mod of z by 3, let's check that also. Mod of z by 3, mod z is less than 2, so this is 2 by 3, and 2 by 3 also again itself is less than 1. So mod of z by 3 also comes out to be less than 1. Let's expand now. 2 by 3, 1 minus z by 3 plus z by 3 whole square, so on, minus 1 by 2, 1 minus z by 2 plus z by 2 whole square, and so on. Now collecting the terms having the same powers, this is equal to 2 by 3 minus 1 by 2 plus minus 2 by 9 plus 1 by 4 z plus 2 by 27 minus 1 by 8 z square, so on. Finally 1 by 6 minus 1 by 36 z minus 11 over 216 z square plus 49 over 1296 z cube, plus so on, which is valid for mod of z less than 2. Fine? Okay. Show that 1 by z square is equal to 1 plus summation starts from n equal to 1 to infinity n plus 1 into z plus 1 the power n for mod of z plus 1 less than 1. Now my expansion should be now in 1 minus mod of z plus 1. So what we are having in the denominator is z square only. We need z plus 1. So what we have to do is adding and subtracting 1. If you take minus outside and collecting z plus 1 whole, so minus sign will be compensate with this square and become positive. So 1 over 1 minus 1 plus z whole square. Is this comes? Yes. So which is equal to taking the denominator in the inverse form. 1 plus, we expand this series because it is already given that mod of z plus 1 is less than 1. So I have expanded the series. Now the result. Take 1 as it is And now summing up the rest of the terms. Now from where n starts from? See, if this is 1, this will be 2. So if this is n, this will be n plus 1. Right? So if you put n equal to 1, you will be getting this second term. Then for n equal to 2, you get this third term. So n should be start from 1 up to infinity for mod of z plus 1 less than 1. Right? Next. If mod of z is less than 1, show that 1 over 1 plus z square into z plus 2 is equal to 1 by 10, this summation, plus 2 minus z by 5 into this whole summation. Now, denominator is in the form 1 plus z square and z plus 2. What we already do is, we separate this 1 plus z square as z plus iota into z minus iota and taking z plus 2 as, right? But we need not have to separate this 1 plus z square in this iota form, because in our result we need the power, see, the first term having the power only z, the power n, and for the second term we need the power z square into n. So we need this z square, right? That's why we should not separate this 1 plus z square into iotas, because we need z square in our result. Alright? So just we need z plus 2 and 1 plus z square. Don't separate this, right? Okay, if z plus 2, take z plus 2 equal to 0, what will be your z? Minus 2. Put minus 2 in the rest of the part, we'll be getting 1 over 5. Now what about this term? You have to think about the term so that on taking your LCM, so that if you take your LCM, your numerator on simplifying comes out to be 1. You have to take that term. That means if you take the LCM, that is 1 by 5 into 1 plus z square plus z plus 2, I don't know this, z plus 2 into 1 plus z square. Now 1 by 5, we need here numerator 1. So this is 1 by 5, on multiplying this will be z square by 5. Here it is z, so I need obviously z by 5, right? But this is positive z square by 5, I need negative z square by 5, so that they will be cancelled. So I can write minus z by 5. Okay, rest, then this is minus z square by 5, then this is minus 2z by 5. I need plus 2z by 5, so that will be cancelled. So for plus 2z by 5, I should write here plus 1 minus 2z by 5, and then this is z, so I should get here 2, yes. Alright, let's simplify, let's check. This is 1 by 5, this is z square by 5, this is minus z square by 5, this is 2z by 5, and then this is minus 2z by 5, and then it is 4 by 5. So these two cancel and these two also cancel, left with 1 by 5 plus 4 by 5, that is 5 by 5, which is nothing but 1. Alright, so on simplifying, I will be getting my numerator to be equal to 1. So what is this term now? This term is 2 minus z by 5. Okay, so you should have to think like this. Sorry. So this term should be 2 minus z over 5, right? Now taking this 1 by 5 as like this, 1 over z plus 2 plus taking this 1 by 5 as 2 minus z over 1 plus z square. Now we need here 10, so take this 2 common. This is 1 by 10. This is 1 plus z by 2. Plus, we need 2 minus z by 5 outside. So take this 2 minus z by 5. And inside we are left with 1 over 1 plus z square. Now taking this denominators in the inverse form and get ready to expand, but in summation form. Okay. So this is 1 by 10, 1 plus z by 2 inverse, plus this is 2 minus z over 5 and 1 plus z square inverse. Now we need not have to expand this, just we have to write the expansion in the summation form. So this is 1 by 10. You can check your remarks. In summation form, this expansion will be n going from 0 to infinity minus 1 the power n into z by 2 the power n. This is 2 minus z by 5, summation going from 0 to infinity minus 1 the power n into z square the power n. Finally, 1 by 10, summation going from 0 to infinity minus 1 the power n z the power n over 2 the power n plus 2 minus z by 5, summation n going from 0 to infinity minus 1 the power n z the power 2n. This what we need is, okay. Here ends up the examples. Now in the next session we have some theorems, that is Morell's theorems, Leibniz theorems, Cauchy's inequality. All these are remaining. So do subscribe my channel for the latest videos. In the next video I'm doing the theorems, and if you need the real analysis course, you can check the description box for that. And thank you for watching the video. Do subscribe the channel.